Welcome to Brain Vision.
Hello everyone. So today we are going to solve this problem. This problem is of a nuclear decay through alpha emission, where uranium-238 is the starting element we have. Uranium-238 that decays into thorium-234 and an alpha particle. So what the problem asks us to do is to find the total energy that is released by this process. So how do we do that? So first of all, we need to know that in these kind of nuclear reactions, what happens is the total mass that you start with on the left is slightly more than the sum of all the masses that you have on the right. So to first calculate the energy released, we need to first find how much is the energy that has been lost due to this transformation. How do we do that? We find we add up all the masses on the right and subtract all the masses on the left. Now we have been given these values here in the problems, except the mass of a particle, which you can look up in Wikipedia, is this 4.001506 U. You need to have a big accuracy of the digits because in these kind of reactions, the mass difference is really small, and that little mass difference actually gives rise to a lot of energy as we'll see right now. Okay, so let us find the mass difference then. So the thorium mass is 234.043 601, and alpha particle, as we just saw, 001506, and uranium mass is 238.057 sorry. Okay, let's do this math. I will use my calculator and you can use yours. So it's 234.043601 plus 4.001506. That is 238.045107, and what you have on the left was 238.050780. See, the total mass that you have on right is little less than what you have on right, and it's like 1/100th of an atomic mass because this is given in U, atomic mass unit, the standard mass unit. Okay, and how much will that be then? Let's subtract 238.050788. That comes out about minus 0.00561 U. Okay, that's the mass you get. So that much of mass has been lost, and that mass isn't really lost, that mass just got converted into energy. And how do we know how much energy that it generated? For that, we need to use the famous Einstein's equation. So let's go there. That says the energy generated when some mass m is destroyed is given by m times c square. Okay, right? Now, there is you need to deal with various units. So as you can see in the first page, here you have the mass in atomic units, and so what we have here is just a direct conversion of the mass into energy given the speed of the light. So an easier way to do this when you have the mass given in just the atomic units will be to use the direct conversion, and for that we have it right here. You can look that up too. 1 U when destroyed gives rise to 931.5 MeV of energy. So this is like theory that you can look up. So when one U of mass is destroyed, this is the amount of energy that is released through this equation. As long as you know that, you can just use this formula and put in that how much energy would be released when zero point zero 0.05, yeah, 0.05 00561 5681 of U, let's put this, is equivalent to how much energy? You need to multiply this with 931.5. That gives you 5.2918. Let's stick with this one. Oh, sorry. Yeah, since we had just one significant digit here, 931.5, we'll stick with just one. That will be about 531.9 MeV, right? And see that we had a negative sign here, and finally, so we carry out a negative sign. So that's the amount of energy that has been released. So the problem doesn't ask which units do you need to mention them, so you can just leave them in MeVs. So, and what does the negative sign imply? It says that the reaction that you see here is an exothermic one. So, like, it releases energy, and by the end of it, you have this much of energy left, and that's why it's a spontaneous one. So, uranium decays into thorium spontaneously. Okay, now let's go to the next problem. Next part. What does the next part say? It asks you for the recoil velocity of the uranium thorium 234 nucleus. Okay, so imagine this, like this was a uranium nucleus sitting here, 238. What happened is, like, it got transformed. It formed a little smaller uranium 230, no, thorium 234 nucleus, and an alpha particle, which is a mass 4. It kind of broke off like this, and this flew off in this direction, and this flew off in this direction. Some kind of explosion happened, and you end up having two pieces of this big nucleus flying off in different directions. So what we need to find is this recoil velocity. That's what it means by recoil. So it's sitting at rest first. That's the assumption we start with. And as it's like a bomb that went off, and when it went off, it asks you for the recoil velocity of thorium. So for these kind of problem, you have to use the conservation of linear momentum. Conservation. Sorry about my handwriting. Okay, so how do you do that? So you started with, okay, what does that say anyway? It says the total momentum stays the similar, right? So how much momentum do you have in the left? You have this particle is sitting at rest, so you have zero momentum. Some mass, but no momentum. Zero velocity, so no momentum, zero. And so what should we have on the right? We should have zero momentum again. And how do we do that? Let's assume it's going with V1, and this is going with V2. So, right, yeah. So M thorium into, rather, V thorium and V alpha. Alright? Yeah. So V thorium plus M alpha, V alpha, we need to find V thorium equal to minus times, if you just rearrange this, oh, that seems like wrong. Okay, and alpha V alpha and thorium. Let's keep this here. Okay, so yeah, let's keep this here. Now, what you see, you need the total. Yes, you need the total mass, a total velocity of the nucleus, of the alpha nucleus moving to. Otherwise, you can't have it. You can't solve for the V thorium. So how do we find that first? For that, we need to go further into energy conservation. And what does that say? Let's go next. So it says that the total energy is conserved. Like the energy that came out of the reaction actually went into accelerating, like putting these two things in motion, two particles in motion. Okay, and so, all right, and let's try substituting that here because we need to find V thorium, right? So, okay, let's do other way around, or V alpha equal to minus m thorium over m alpha. We can substitute this here. How do we do that? F m thorium square plus f and alpha minus times, yeah, m thorium alright, m thorium v thorium by m alpha square. Okay, the negative sign falls off due to the square. Okay, let's put all of this together, and if you simplify, what are you left with is m thorium v thorium square 1 plus, right? Yes, right? See, the power cancels m alpha, so you're left with just this now. And we know this will be the delta E, right? So if you can put everything back here, so now you also need to change the units because this was in 931 MeV, right? Okay, so let's go back there. So what does it say? Yes, so you see, we use this formula here, this formula. What does it say is like when m is expressed in u and v is expressed in a fraction of c, so your energy is comes out in MeV, right? So come back here, we'll use this trick here, right? So let's do the math here. How much was that? Yes. minus 5.3, right? All right. But take care of the negative sign now because you have a square here. So what happens is that this is the magnitude of the the energy that is produced of the reaction, and that would be minus 5 point. Oh, sorry, you don't have the minus. Keep it away. Yes. Okay. MEVs, and this is mass of thorium. Uh, sorry about it. Hold on. Yeah. So the trick what we use here of having it in MEVs, we can go back here, talk the in terms of U, right? See, I'm taking the time just to convert the units. It's important, otherwise your math will be messed up. So what you do here, you use this value. We use this value here finally. So energy can be expressed in mass also. As you can see, E equal to mc square. So 0.005681, right? Okay. But as I said before, you don't need the negative sign because we are talking about the magnitude, total magnitude of the energy, equal to half. And now we put everything back again. How much is the mass of thorium? That is, yes, 234.043601, right? Alright. And that is 3 thorium square, and 1 by 1 plus, what is the mass of alpha we used? Plus 4.001506. Alright, so finally, I hope it's clear that it's a half. Alright, yeah. So if you rearrange everything, we just need to solve this equation. This is the only unknown that is left. And what you will get here out of here, since this is, okay, I didn't mention this here. So it is said MeV per C square. That's the, yes. So when you use this conversion unit, the answer that the result that you will finally get would be in fractions of C, as I said mentioned here, right? In a fraction of C. All right. So I'll do the math for you. How much do you get? Yes. Let me put everything back. Five, six, eight, one. 234, 234.043601. That is 517.021800, right? How much will this be? 1 by 4.001505. This will be 1 plus something. 1.24990. number, 3 digits, 6,990. Alright, so finally V thorium square would be 217.218. This is not good. 29.24447, right? And how much that gives you? Yeah, 0.00568. Thorium is square root of 0.1114, right? That's it. Alright. So you need to find this. Yes. If we take a square root here, what do you get? Point oh one four. C. See, as I told you here, you get the answer, you get it in terms of a fraction of C. So, so the final speed that you get, the recoil velocity, that says that it will be, that means this is equivalent to saying 1.4% of C, the speed of light. Right? So that's it. I should do it. That's your answer, finally. So let's revise the steps once. What happened finally is that your uranium 235 got decayed into thorium and alpha particle, and what happens basically is that the uranium part, the mass of uranium, a little bit mass out of uranium decays, and that gives rise to the energy. And how do you find it? Find how much energy decayed? So you subtract the total mass on the right from the total mass on the left, and you are left with a negative sign, negative value of some atomic mass in terms of atomic mass. Now to find the energy, you you use the Einstein's relation of E equal to mc square, which says that every U of atomic mass when destroyed gives rise to this much of energy. So we have this much of it, and that will be then our answer. 5.3 MeV of energy has been produced in this reaction. Now, the problem asks you about the recoil velocity of thorium. How do we find that? So for that, you need to use first of all conservation of momentum, because we assume that the uranium nucleus was sitting at rest, and as a result of the reaction, it got split into two, the thorium and the alpha particle, which both flew apart in two different directions. But they have to conserve the linear momentum. You started with zero linear momentum, and so you have to have this finally. The total momentum of both of the particles should add up to zero. When we use this theorem, when we use this, we get back the velocity of alpha in terms of the velocity and masses of thorium and alpha particle. Now, what we do is we write down the expression for the energy, and here we see there is no potential energy. All the energy that has been generated out of the reaction goes into the kinetic energy of the particles, and these are the formula of the kinetic energy. We do assume that the speed of the particles are much more less than the speed of light, so that we can actually use this formula. And when you substitute everything back from here, the velocity of alpha particle, because that's not what we want, we just want this value, the velocity of thorium. You can rearrange everything, put the values, do the math, and finally you get the answer in terms of a fractions of c. What that means is this will be the recoil velocity, 1.4% of the speed of light. That will be it. Thank you.